Hi, this is Team 37's CS426 Senior Project, developed in the Computer Science and Engineering Department at the University of Nevada, Reno, from 2023 to 2024. The first section that we will be demoing is robot localization, mapping, and movement. In order to localize the robot, a global map is created using SLAM mapping techniques and is visualized using the RViz software as seen in the clip. Now that the robot is localized and knows where it is as reflected in the still frame shot, it is time to move on to movement. The RViz software allows us to emulate this movement and tell it where we want it to move and in what direction it will finish in. After it officially finishes its localization, it takes off to the end goal position and point. It chooses the optimal path to get to its goal position, as well as using the LiDAR camera to avoid objects and prevent collisions. Here is a more close-up view of the RViz software as the robot takes the optimal path to the selected goal location and direction. As you can see, the robot knows where it is located on the global map, and it shows itself moving on the display, as well as updating the local map based on any updates or changes. This would not be possible without the LiDAR camera, which came pre-installed on the Highwonder Jet Auto Pro Ross robot. It allows us to detect the objects in its surrounding area, and it is extremely useful for mapping and collision detection as seen in this video, as the robot veers left around the backpack that is laying on the floor. This is pivotal for our project because spaces get messy and the robot needs to be able to navigate around objects such as shoes, wallets, keys, and anything else that may be laying around.
The next integral part of our project is the object recognition module, which enables our robot to perceive and understand its surroundings by identifying objects within their environment. We are using YOLO, which is a deep convolutional neural network, and there are many versions of YOLO, but for our project purposes, we decided to use YOLO v3. So now we are going to see a demonstration of this part of the project. We are also going to notice that there are some objects that are identified and they are not correct, or there are duplicates, but this is a feature that is going to be taken care of through the user interface. Let's see how this works. On the right side of the screen, we have the autonomous navigation of the project, and on the left side is the object recognition. So now the robot starts moving autonomously, and it also sees its surroundings and identifies a couple of objects, which are going to then be sent to the user interface.
Hi, I'm James. I'll be talking about the UI portion of the project. I'll show you a demonstration of the UI running on the robot while I explain some of its more important characteristics and design components. We chose to use a web-based UI for two main sets of reasons. One, accessibility, and two, technical advantages. Starting with accessibility, it lets users use pre-existing browser-based accessibility tools like screen readers as they interact with our robot. It also enables them to access the UI from any sort of computer or hardware. One of the big technical challenges of this project is memory management. The mapping and object recognition systems use a lot of RAM memory. On the UI side of things, we work to ease this memory use. When the robot detects an object, say a cup, it immediately sends that data over to the UI, where the UI will check on the client-side device how confident the robot is that what it saw is a cup. And so if it's decently confident, then it keeps that data and displays it to the user. Otherwise, it throws that data away. And by doing this, the robot doesn't have to store data about the cup. The only data that's stored over a long period of time on the client side is just the data the user would want to see. The technical tool that helps the UI do all this is called RossLibJS. It's a JavaScript library that can listen and publish to ROS topics, as well as make ROS service calls. It can listen to the ROS topic from the object recognition system to receive that data, and then we can transfer that into an object in JavaScript that we can process and parse. We eliminate duplicate object detections The thresholding does much of this for us by nature. It eliminates any low-quality duplicates from the dataset. Then we can display the objects detected to the user. We have a list of items and text on screen, so any screen reader could pick it up. Finally, the UI has several buttons. One of them clears the screen of items that the robot has detected. Another tells the robot to start its process of navigating and identifying objects in a room. And another tells the robot to stop whatever it's doing.
Once again, we are Team 37, the RoomSense robot. Thank you for watching.